This video is about the fundamental theorem of line integrals. I'm going to tell you what the fundamental theorem of line integrals says. I'll show you how to use it. We'll do a brief proof. It's actually pretty simple. And then we'll look at three equivalent conditions. And as part of our discussion, we'll also define connected regions. So here's the theorem. The fundamental theorem of line integrals, which I will abbreviate this way from now on, says this. It says, let C be a piecewise smooth curve lying in an open region R. So we've got a region, let's just say we're in two-dimensional space. Yes, we could have an open region R, or Q is what we've been using in three-dimensional space, but it's still an open region. But for our picture, let's stay in 2D. So we've got some open region R, so that's a region that doesn't contain its boundary. And C is a piecewise smooth curve, and it's lying in this region. So maybe as T increases, we go this way. So we start here at this point at T equals A, and we end here at this point when T equals B. So we've got a piecewise smooth curve lying in this open region R, or Q if we're in space, given by R of T, and T ranges from A to B. It says, the theorem says, if F is conservative in this open region, and its component functions, M and N, or Mn and P if we're in 3D, are continuous in that region, then this line integral of F dotted with dr, that line integral that represents work or it represents flow, depending on whether F is a force field or the velocity field of some fluid, or if it doesn't represent one of those, if it represents something else entirely, this line integral is equal to this. And that's because F is conservative. And here's the kicker. All you have to do to evaluate this line integral is find the potential function F, the potential function F for the field capital F. Evaluate F at the end point, evaluate F at the start point, and subtract. I don't know about you, but I think that's really cool. Remember all that work that we did in the last few videos? We had to come up with a piecewise smooth parameterization of C. We had to find R prime of T. We had to find F as a function of T. We had to take a dot product and then evaluate an integral. That's not too bad. I mean, it's doable. We have all the skills that we need in order to evaluate something like that. But this is nice. This says all you have to do is find the potential function and evaluate the potential function at the end point and the start point and subtract. Notice the similarity between that and the fundamental theorem of calculus, or one part of the fundamental theorem of calculus. Remember this? I'm going to write it a little differently. The integral from a to b of f prime of x dx is this. We take the antiderivative of f prime to get f. Then we plug in the endpoint and the start point, and we subtract. Look at that, it's very similar. So that's what we're saying here. We're saying if your field is conservative and C is a piecewise smooth curve lying in an open region R, and the function is continuous in that open region R, so that means all the component functions of the field are continuous, then all you have to do is find the potential function and evaluate it at the end point and the starting point and subtract. So I think that's pretty nice. And it gives us options. You can evaluate the original integral, line integral, using the techniques that we talked about in the last few videos. You can find the potential function and evaluate it at the end point and the start point and subtract. Or you can take a different path. Instead of going from A to B along this path, I could go along a straight line path and everything might be simpler. Now there's another qualifier there. If I want to take a different path, the following is required. This region R has to be what's called a connected region, and I've drawn a connected region here. So let me define that for you. we say a region is connected and this is true in the plane or in space. And I think probably in n dimensions as well. A region is connected if any 2 points in the region can be joined by a piecewise smooth curve lying entirely in the region. So let's say I've got a couple of regions that look like this. So there's one region. Oops, there's region. I'll call that R. And then I have another region R. And let's say we've got another region R. Okay, so this is R. I guess we should label them differently. We'll call that one R1. We'll call this one R2, and we'll call this one R3. R3 consists of this region out here in this little island inside. Okay, the question is this region connected? Well, it's connected if any 2 points in the region can be joined by a piecewise smooth curve lying entirely within the region. So if I have a point over here and a point over here, isn't it possible for me to draw a piecewise smooth curve from there to there? Saying yes, okay. Well, that still doesn't prove anything. That has to be true for every 2 points in the region, any pair that we choose. Is that true for any pair? If I plot a point here and I plot a point here, will I be able to draw a piecewise smooth curve between them? I sure will. I could just draw straight lines, couldn't I? I'd be able to make that work. What about this one and this one? Well, that's okay. I can just make it curve a little bit. It still lies in the region, right? So this one is connected. What about this region? If I select this point in the region and a point over here in the region, obviously I can connect those with a piecewise smooth curve. But what about here and here? That's fine. It doesn't matter, right? Even though there's this little hole in the middle, I can still connect any 2 points in the region by a piecewise smooth curve. If I wanted, a lot of the time, I can just connect it by a line segment, and that's going to work out fine. There are no points that are in a little part of the region that are isolated from the rest of them. So this is connected. What about this guy? Now if I pick 2 points in there, they're fine. I can connect those with a piecewise smooth curve. But what if I select 1 point in there and 1 point over there? Can I get from that point to that point without leaving the region? No, we're gonna have a problem because we have this little island thing, right? So this is not a connected region. It consists of 2 parts. It's this part and this part. And the same would be true if it looked a little different. If my region was like this region and then this adjacent region. What if I called this region 4? That's not connected either. Because if I have any point on this little island and any point on this little island, I'm gonna have to leave the island to get to the other one. So neither of these are connected. Okay, now that allows us to state one additional fact. If our field F is continuous in an open region, so that's a region that does not contain its boundary, and it's a connected region. So it feels connected. It's sort of all in one piece. Like that's all in one piece, that's all in one piece, that's two pieces, that's two pieces. Those aren't connected. If that's true, then to say that this integral is independent of path, or I'll call it path independent, if and only if f is conservative. So that's nice. And I think that's what I wanted to get at here when I was looking at the fundamental theorem of line integrals, but I had to add that extra qualifier. We needed to say that our region was not just open, but open and connected. So now let's go back to the fundamental theorem of line integrals again. So here's the fundamental theorem of line integrals. It says, if C is a piecewise smooth curve, it lies in a region R, or Q in space, and it's given by this parametric representation. It's a vector valued function R of t for t between A and B. If f is conservative in that region, in the plane or in space, and its component functions are continuous, then the line integral over f is just the difference in the potential function at the endpoint and the start point, and we subtract. Now, as long as our region is connected like this, well, there are lots of different paths that I can take from A to B. If this is my region, I could take that path, I could take this path, which is pretty simple. I could take this much more complicated path. I don't know why I would do that, but I could. But the line integral over all of those paths is going to be exactly the same. I start at the same point, I end at the same point. If I can connect that, if I can connect those 2 points with a piecewise smooth curve, and the whole time my field f is conservative and its component functions are continuous, then it doesn't matter which path I take. I can take this path or this path or this path. So if I'm in a connected region, we say that this line integral is path independent. I've got options. I can evaluate the original line integral. I can evaluate the line integral over this curve instead, and I'll get the same thing. Or I can say, I don't want to do a line integral. I just want to find the potential function, plug in the endpoint, plug in the start point, and subtract. So that's pretty cool. Let's actually use this to evaluate a line integral now. And we'll do this over several paths. So let's say this is your field. And let's stay in the plane for right now. This makes computation a little bit easier. So you've got this field and someone asks you, hey, why don't you compute this for me? Compute the line integral over C of that vector field F, where C is this curve. And we're going to do this over several curves, so I'll draw this way. It's a line segment from 0, 0 to x equals 1, y equals 2. And then let's go over here. So we're on a circle of radius 1. And we end up over here at this point. That's x equals 3, y equals 2. Okay, so that's our curve C. Now, if we want to, we could parameterize this curve. We could parameterize it in 2 pieces. I could find a parametric representation for this piece and this piece. And I could evaluate the line integral using the curve that was given to me. And I call this the curve C1. And if the field's not conservative, that's what I have to do. I have to find a parametric representation for this. I have to evaluate this in terms of t, given my parametric representation of x of t and y of t and x of t of and y of t there. And I'm going to take a dot product, and then I'm going to integrate from t equals a to t equals b. And since we've got two pieces, we're going to have to do that twice, then we add them together. That's what we would have to do if the field is not conservative. But if the field is conservative, we've got options. We can evaluate this line integral. We can evaluate this line integral. We can find the potential function of the field, and then just evaluate the potential function at 3, 2, and evaluate the potential function at 0, 0, and subtract. All of those are options if the field is conservative. If the field's not conservative, we're stuck and we have to do the line integral the traditional way. So we've got a 2D field. Let's see if the field is conservative. So I'll call this component M and this component N. The first thing we do is test F to determine if it is conservative. Actually, I'll keep this over here and I'll move my camera. There we go. Okay, so we know this field is conservative if the partial of the x component with respect to y is equal to the partial of the y component with respect to x. So let's compute those. Well, if x is being treated as a constant and we're differentiating with respect to y, I've got a constant x here, so I bring that down, and then I take the derivative of y squared, which is just 2y. Now let's look at the partial of n with respect to x. That's the partial of the y component with respect to x. Question is, do we get the same thing? Oh, I don't think we do we? Let's get rid of that too. I want it to be conservative, so let's get rid of that too. What's the derivative of this with respect to x? Well, now y is a constant. The derivative of x squared with respect to x is 2x. The derivative of e to the y with respect to x, if we're treating y as a constant, is 0. So when I got rid of the 2, now I've got a conservative field, and that's nice. So now I don't have to evaluate this line integral that way. I can evaluate the line integral from here to here instead, which would be pretty simple to do. Or I can find the potential function of my field and evaluate it at 3, 2, the end point, and 0, 0, the start point. And I guess we needed some arrows to indicate orientation. If we're starting here and we're ending here, and evaluate the end point and the start point and subtract. And either way, any one of those 3 ways, and actually any one of the infinitely many paths that we could take to get from 0, 0 to 3, 2 would give us the same result, provided that this function is continuous. And this function is continuous in the entire xy plane. We have no problem with continuity for m or n. So I could take any path I wanted from 0, 0 to 3, 2. I could take some wild path over here. I could just take an adventure all around the xy plane and then come back to 3, 2, and you're going to get exactly the same result for this integral. Okay, so we know the field's conservative. We can evaluate this through any number of methods. I don't think I want to evaluate the line integral over the original path. We've already done that before. Let's evaluate the line integral over this new path from 0, 0 to 3, 2. So here's one method for evaluating this. If this is C1, I'll call this new path C2. The integral over C2 of f, or C1 of f, is equal to the integral over C2 of f. So I just need a piecewise smooth parameterization of this line segment that starts at 0, 0 and ends up at 3, 2. So C2 can be written this way. So we can let, well, we're in the plane, so R of t has components x of t and y of t. Now, if we want to, we could let x equal t, and then let t go from 0 to 3, and then y would be, well, y is equal to 2 over 3 times x. We could end up there. There's an easier way in this case. I'm not going to do that this time since it's a line segment that goes through the origin. If I let x equal, or if I let t go from 0 to 1, and I let x equal, well, I'm going 3 units in the x direction, 3t, and I let y equal 2t because I'm going 2 units in the y direction, that's going to trace out that same curve. You don't have to do it this way, but this is helpful, I think. Since it's a line segment, I just use the direction vector. We go 3 units in the x direction, 2 units in the y direction. And I multiplied the direction vector 3, 2 by t. And since we're starting at 0, 0, there was no x naught or y naught. I think this is simpler. It just allows us to avoid the fractions. So this is one way that we could represent R of t. Well, in order to evaluate the line integral over C1, we're saying instead of doing that, let's evaluate the line integral over C2. So this is C2. We found a piecewise smooth parameterization of C2. The next thing we would do is find our field in terms of t, because if I'm on that path, my field depends on t while I'm on that path. My field it really depends on x and y. But if I'm going along that path, it's almost as if my field depends on t. My field was given by x squared y plus x, or xy squared plus x, and x squared y plus e to the y. And now I want to evaluate this at x of t and y of t. And x of t is 3t and y of t is 2t by design. So I've got x times y squared plus x, and then x squared times y plus e to the y. And x is 3t, and y is 2t. And so after we do a little bit of arithmetic and algebra, I've got a 4 times 3, which is 12. And that'll be a t squared times t is t cubed. And then I've got 9 times 2 is 18, t cubed. So I've got my field in terms of t. Excuse me. And then the next thing I need to do, remember to evaluate this. This will be the integral from a to b of f, evaluated at x of t, y of t. And remember, dr is r prime of t dt. So we need to find r prime, and we need to dot it with f, where f is written in terms of t. Well, r is pretty simple. So r prime is pretty simple. Derivative of 3t is 3. Derivative of 2t is 2. So we compute r prime. And then we dot these. We take the dot product of f with r prime. So I'm multiplying component by component. I take the x component of f and the x component of r prime, and I multiply them together. And then I take the y component of f and the y component of r prime, and I multiply them together. Remember, that's how dot products work. We multiply and add until we have no components left, and then we stop. So I've got 36t cubed plus 9t, and looks like 36t cubed plus 2e to the 2t. So I've got 72t cubed plus 9t plus 2e to the 2t. And that's going to be my integrand. Then we'll set up and evaluate the integral. So the line integral of f over c1 is the same as the line integral of f over c2. And our bounds for c2 were chosen to be 0 to 1. Your bounds might be different. Your x of t and y of t might be different if you parameterized it differently. But we're going to get the same answer for our line integral if both of us did our parameterization correctly. Okay, so we integrate from 0 to 1, and this is our integrand. I just want to show you that you get the same answer using the potential function. So we'll do it this way, and then we'll do it with this potential function as well. Okay, so we're just anti-differentiating. Bring your 72 down, add 1 to the exponent, divide by the new exponent. Bring the 9 down, add 1 to the exponent, and divide by the new exponent. Bring the 2 down. The antiderivative of e to the kt is e to the kt, and then you have to divide by k. If we're differentiating, we'd multiply by 2. If we're anti-differentiating, we divide by 2. Then we evaluate from 0 to 1. Now 4 goes into 72 18 times. So it looks like we're going to get, when t equals 1, 18 plus 9 over 2, so that's 4.5 plus e squared minus, if we evaluate this at 0, we get 0 plus e to the 0, which is 1. So we end up with 22.5 minus 1, so it's 21.5 plus e squared. That's our line integral. Okay. Since the field is conservative, the line integral over C2 is equal to the line integral over C1, and it's equal to this. So that was one option. We could have done the line integral over C1, we would have gotten the same answer. Line integral over C2, we get this answer. Now the third option is to say, why don't we just use this? We know the field's conservative. Let's find the potential function, evaluate it at 3, 2, evaluate it at 0, 0, and subtract. We should get the same thing. Let's do that. We skipped that first method because it wasn't an integral I wanted to evaluate. Not that I mind, but there was just a more efficient way. Okay, so our field was this. It has components x, y squared plus x, and x squared y plus e to the y. Now, since this field is conservative, and we already checked earlier, this is conservative, then this is m, and that's n, and that's equal to the gradient of some function, little f, for some f. The only way these two vectors are equal is if the components are equal. So the partial of f with respect to x must be x y squared plus x. And the partial of f with respect to y, well, that's the y component of this, must be x squared y plus e to the y. Now I can use those two pieces to recover f partially, and then I can compare them to each other and figure out what f is in general. Okay, so I have the partial of f with respect to x, and I want to find f. So I take the antiderivative of the partial with respect to x with respect to x, and that will recover f partially. It's sort of a partial antiderivative. Okay, so I'm anti-differentiating with respect to x. Y squared is constant, and the antiderivative of x with respect to x requires the power rule. So I add 1 to the exponent and divide by the new exponent. Over here, same thing. Antiderivative of x with respect to x, add 1 to the exponent and divide by the new exponent. And then I have to add a function that's constant with respect to x, but not necessarily with respect to y. So I'll call that g of y. And typically, we'd write this alphabetically. And if you don't like these 2's in the denominator, you can pull out a 1/2, that's fine. So that's f of x, y. It's this plus some unknown function g of y, and I'd really like to know what that function is. To figure out what that function is, I will try to recover f a different way. I'll take the antiderivative of the partial of f with respect to y with respect to y. So we bring the x squared down, that's constant. And then we anti-differentiate y to the first with respect to y. So we add 1 to the exponent and divide by the new exponent. The antiderivative of e to the y with respect to y is e to the y. And then we add something that's constant with respect to y, but not necessarily with respect to x. So I've got that. Now these two functions have to be the same. So I'm matching now. I'm looking for f of x, y in general. I know it's this plus some function g of y, and I also know it's this plus some function h of x. I just need to figure out what h of x is and what g of y is. If I know those, then I know what f is. And through comparison, through saying, hey, these are really the same thing, just written in a slightly different form, I should be able to figure out what f is. So I'm looking at those, and I'm comparing, and the first thing I'm doing is saying, well, what do they both have in common? Well, they both have that x squared y squared over 2, and I don't like that 2 in the denominator, so I'm going to pull it out as a 1/2. So I've got an x squared y squared times 1/2, so that's the same. Now I'm going to focus on the part that looks different. They're not actually different, but they look different, and I'll figure out what h of x and g of y must be. Well, this function of x plus g of y must equal this function of y plus h of x. So I think, well, h of x must be the x squared over 2, and g of y must be the e to the y. But we also need a constant of integration, so g of y must be this plus a constant, and h of x must be this plus the same constant that we had for g of y. So let's add those two pieces. Since this is here and this is here, I'll have 1/2 x squared plus e to the y plus some constant of integration, which I'm going to call k. Now, check and make sure it works. Is this the same as this? Do I have that term plus a function of y, e to the y times, or plus k? Yep, that works. And do I have this as well? This plus a function of x. 1/2 x squared plus k, that's my h of x, yes. So this is my potential function, but whenever you're using the fundamental theorem of line integrals, it's just like the fundamental theorem of calculus. If I'm evaluating this at one point and evaluating at another point and subtracting, I don't really need the plus k, because I'm just going to end up with a k minus k is 0. It's going to go away. So given that, now let's use this to evaluate the line integral. So the line integral over C1 of f dotted with dr is the line integral of the gradient of little f dotted with dr. Well, according to the theorem, that's equal to f of xy evaluated at the end point and the beginning point, and we subtract. And f of xy is this, and I don't really need my k. So I'll say 1/2 x squared y squared plus 1/2 x squared plus e to the y. And I'll evaluate that at 3, 2, and I'll evaluate that at 0, 0, and subtract. So at 3, 2, let's see, what do we get? 3 squared, 2 squared, plus 1/2, 3 squared, plus e to the y, so that's e squared. And then when x and y are both 0, we get 0 plus e to the y. And e to the y is e to the 0, so that's 1. Okay, one of those 2's reduces with that 1/2. So we have a 9 times 2 is 18, plus 9 over 2, plus e squared minus 1. You recognize this? I'll flip over the page or show you in just a second. We get the same thing before. That's 21.5 plus e squared. When we evaluated the line integral over C2, look what we got. We got this. 18 plus 9 over 2 plus e squared minus this. That was exactly what we got when we used the fundamental theorem of calculus on this, and this came from this parametric representation of C2, so the line integral over C2. Since the field is conservative, instead of going along this path, we went along this path, we got the right answer. Or we said, let's avoid path integrals altogether. Let's avoid line integrals altogether. Let's just find the potential function, and we did. Then plug in the endpoint, plug in the start point, and subtract, and you get the same value. So that's an option for you. Isn't that cool? I think it's cool. Okay, so now that we've got our potential function, well, we can find the line integral of this function over lots of different curves. Let's say we want the line integral of this function over this interval, or over this curve. So that's a semicircle of radius 2, and let's say our curve is being traced out this way. So I'll call this C3, and it's just this part. Two options, or three options here. Because the field is conservative, and it's the same field from before, oops. So we've got that same field from before, that conservative field. Here are your options. Method number 1. You can just evaluate the integral that they gave us. And that means coming up with a piecewise smooth parameterization of C3. Well, it's a semicircle, it's not so bad. We know the parameterization of a circle is typically cosine of t for x and sine of t for y. That's a unit circle. And that's usually being traced out in the counterclockwise direction. If we go clockwise, I just switch the sine and cosine. And the radius of the circle is 2. Okay, now we don't get the whole circle. This would trace out the entire circle in the counterclockwise direction infinitely many times as t goes from negative infinity to infinity, but I only want to trace out this portion once. So this is, we're starting here at x equals 0, y equals 2. So I think we could start with t equals 0, and that would work. And then we end up over here at x equals 0, y equals -2. Well, the next time sign would be 0 is at pi. And at that point, at that time, cosine of pi, that's -1, so we'd get -2. Makes sense. Our angle is just a single t. So I'd expect to go through the same number of radians that I see there for that part of a circle. I go from 0 to pi. Okay. So then I would have to replace x of t with 2 sine of t, y of t with 2 cosine of t in here. I'd have to take the derivative of this, which isn't bad, just 2 cosine of t, 2 times negative sine of t. Dot that with this, and then integrate that result from 0 to pi. There's going to be a lot of trig functions. It's going to be relatively complicated, but it can be done. We could do that, but I'd rather not. It's going to be a lot more trig functions that I'd prefer. So that's one option. We could do that. Or we could say, I don't like that curve. Semicircles are pretty, but you know it's easier. Engineering students, you know it's more efficient. Like, let's not do that. Let's go straight from there to there. Like, that's the most efficient path from 0 to 0, -2. So evaluate this one instead, since this is equal to this, as long as we start and end at the same place. So if I start here and I end here, provided that this function is continuous, and it is, it's a polynomial function in x and y, and we've got a polynomial function in x and y plus an exponential. Those are both going to be continuous throughout the entire xy plane. Rather than doing this, I could do this, and it's really easy to come up with a parameterization for C2. Or I guess we use C2 for something else. We'll call this C sub 4. Because on that little line segment, x is equal to 0 the whole time. And y runs from 2 to -2. Ooh. Y is going from a larger number to a smaller number. So maybe I want to let t go from -2 to 2. And let y equal -t. Because if y is -t, when t is -2, we'd end up at 2. And if y is -t, when t equals 2, we end up down here. So that's an option. That could work. I just did that sort of using intuition. If you don't want to use intuition, you could say, okay, let's let t go from -2 to 2. And y goes from 2 down to -2. Let's look for a pattern or a relationship between those two. I hope you would see, just from looking at it, that the y value and the t value are opposites of each other. So y equals -t. You could have also used 0 to 4. And then when t is going from 0 to 4, y would go from 2 to -2. And then you could come up with a linear expression involving y. That would work as well. I like this one though. Okay, so this is a really simple parameterization. Then I would just need the field in terms of this parameterization. Gets rid of a lot because there's no x's. There's just y's being replaced by -t. So let's find f of x of t, y of t. So that's f of 0 and -t. Well, if x is 0, that's 0. And if x is 0, that's 0 plus e to the y. And y is -t. So my field is literally e to the -t times j hat. Very, very simple. Now I just need to take this and dot it with r prime. And r prime is very simple as well. It's just 0, -1. So you have 0 times 0, which is of course 0, plus e to the -t times -1. So that's -e to the -t. And we'll integrate from -2 to 2. There's a very simple u sub there. If u is negative t, du is negative 1 dt. And I actually have a negative 1 dt, so that's just e to the u du. That's u, and this together makes du. And then when t is negative 2, u is 2. When t is positive 2, u is negative 2. So we anti-differentiate. We substitute in negative 2 and 2 and subtract. And we get this. Okay, really isn't too bad. We had to find the piecewise smooth parameterization, find f, find r prime, take the dot product, and then integrate. Or you could say, I actually know the potential function for this already. I did that in part A. So we're going to use the fundamental theorem of line integrals and the potential function that we already calculated. I should still get e to the negative 2 minus e squared. According to the fundamental theorem, this is just equal to our potential function, which is on the back of this. It was this function, 1/2 x squared y squared plus 1/2 x squared plus e to the y. And we evaluate at the final point and the initial point, and we subtract. Well, and I think you can see what's going to happen. If x is 0, those are all gone, and we get e to the negative 2. And then if x is 0, these are gone, and we end up with an e squared. That was definitely the most efficient way once we had that potential function. So yeah, you've got options. If your field is conservative, you could do this. And this is really not that bad. We just have x replaced by 2 sine of t, y replaced by 2 cosine of t. Get it, e to the 2 cosine of t, then you compute r prime, you take a dot product, you integrate from 0 to pi, you get an answer. Guess what? That answer is going to be this. So since this field is conservative, I don't have to integrate over that curve. I can integrate over that curve, and we get this. Or even better, I can say since the field is conservative and I already know the potential function because I found it in a different problem, I could do this, and I get that. Okay, now let's look at another one. This is going to look like a trick question. So let's integrate over c, where that's c. I didn't even make it a recognizable function. Well, then our only option at this point is the fundamental theorem of line integrals. And we need to pick a point where we start and stop. So let's say there. Let's call this c sub 5 because we're on our 5th one. Then the line integral of this field over c sub 5 is f at this point, x of a, y of a, actually let's call it x naught, y naught. I don't even know what it is. X naught, y naught, and then f at x naught, y naught, and then we subtract. Do you guys know what the answer is going to be? I almost hate to waste my Sharpie ink. It's 0. That curve is closed. I start and I stop at the same place. Since I'm evaluating the potential function at the same place, when I subtract, I get 0, no matter what location that is. So if you've got a closed curve and your field is conservative, you already know the answer is going to be 0. Now that still holds if that curve looks more familiar. So maybe we have let's say a circle of radius 1, centered at x equals 2, y equals 1. Get a curve that looks like this. Now I could come up with a piecewise smooth parameterization of that circle. I could. And I could basically do what I did here with a slightly more complicated parameterization. But it's closed, guys. We could say we start and stop here at this place. Since the start point and the end point are the same, we're going to get 0. So if your field is conservative, you're going to get 0. All right, that brings us to this next fact. I told you we would talk about what the fundamental theorem of line integral says. We talked about how to use it. We talked about what a connected region is. And we use this idea of connected to talk about path independence. So if our field is continuous in an open connected region, then if f is conservative, then that line integral is independent of path, which means I get to take any path I want from the endpoint or the start point to the end point, and I just do that instead of evaluating over the line or curve that they gave me. And then we just saw, by example, that if our field is conservative and the curve is closed, that we get 0 because you're starting and ending at the same place. So here are the 3 equivalent conditions that I promised you. Now this has a couple more qualifiers. Okay, so let's say that we are dealing with a field F, and so F is a vector field, and we want this field to have continuous first partial derivatives in an open connected region R. When we say that the field has continuous first partial derivatives, we're also saying that the component functions of F have continuous first partial derivatives. We're in an open region, so it doesn't include its boundary. It's connected, so it means it's all in one piece. And this could be in the plane or in space. I'm using R, which we have been using in the plane, but it could be an open connected region cube in space. And let C be a piecewise smooth curve in R. Then we have 3 equivalent conditions. So here's one condition. F is conservative, which means that F is the gradient of some function little f. If F is conservative, that means the line integral over C is path independent or independent of path. I prefer calling it path independent myself. And then if the curve is closed, this is 0. And this is going to be true for every closed curve C. In R. Now again, you could use a parameterization of this circle if you wanted to, and it would be a lot of work, and eventually you would get 0. So if you recognize that the field is conservative, and you see that this curve is closed, then you get to skip a lot. But of course, you'd have to verify that the field is conservative first. Okay. So now let's look at a field in space. And I'm just pulling this question out of the book. I haven't tested this one yet or tried it yet. I'm hoping this one's conservative. So the x component is y e to the z. The y component is x e to the z. And the z component is xy e to the z. Let's say somebody asks you to evaluate the line integral of f over c, where c is given by r of t, and r of t has components 4 cosine of t, 4 sine of t, and 3. Now remember what that would look like. That's a circle of radius 4, and it's shifted up 3 units. So it's just a circle of radius 4 that is 3 units above the xy plane. It doesn't look very circular, but that's the idea. So we're on this circle. Now, if the field is conservative, and we're not actually on the whole circle, we've got some bounds for t. T is between 0 and pi, so we're going to be on part of this circle. When t equals 0, x is equal to 4, and y is equal to 0. So we're going to be at the point 4, 0, 3. And then when t equals pi, we'll be at negative 4, 0, 3. So we're going to start over here, and then we'll end over here on the other side. And between 0 and pi, sine is positive, so y has to be positive, so it's going to be this side of the curve. So we're going this way along our curve. And we're starting here at 403, and we're ending here at negative 403. They've run out of space. Okay. Here's hoping that that field is conservative. Now remember, if you've got a field in 3 dimensions, well, you can't just look at the partial of m with respect to y and the partial of n with respect to x. If you want to tell if a field in R3 is conservative, you have to take the curl of that field. So we'll take the curl of the field to see if the field is conservative. Now, you don't have to write that way, but I like to write it that way to remind myself that it's a vector. Curl. This is a very helpful memory device. You can use this determinant form to compute the curl. Put this del operator in the second row here, and put the components of f in the third row. All right. Cross out the row and column containing I hat. You want to take the partial with respect to y of this, so we get x e to the z. And then take the partial with respect to z of that. We also get x e to the z. That's good, hopeful. We're looking for the curl to be the 0 vector, and those reduce. Almost there, maybe. Cross out the row and column containing j hat. We want the partial with respect to x of xy e to the z, so we get y e to the z. And then we want the partial with respect to z of y e to the z. Also y e to the z, very good, that's 0, hoping here's hoping the last one's also 0. Cross out this row and this column. Partial with respect to x of x e to the z. That's a constant times x. The derivative of a constant times x is just the constant. The derivative with respect to y of y e to the z, that's what we subtract next. Well, that's a constant times y. The derivative of a constant times y with respect to y, that's going to be a constant. Hey, that's the 0 vector. That means our field is conservative. That's going to save us some work. I mean, we could replace x with 4 cosine of t, replace y with 4 sine of t, and replace z with 3. We just have these e to the thirds everywhere. Those are just constants. That's not a big deal. And then we'd have 4 sine of t, 4 cosine of t, 16 times sine of t times cosine of t, which we could reduce with a trig identity if we wanted to. Then we just have to compute r prime for this, take a dot product, integrate from 0 to pi. But now we know our field is conservative. So you have options. If you want, you could evaluate the line integral from here to here. That's going to be a really simple little line integral. Because look, the y and the z aren't changing. The only thing that's changing is the x. X is going from 4 to -4. That's an option. Or you could just find the potential function of f and then evaluate at 4, 0, 3 and evaluate at -4, 0, 3 and subtract. Well, actually, I think I did it the other way around. End point minus start point. So evaluate the potential function over here and the potential function over here and subtract. I think I want to do that one this time. If you're not sure though, you can always do it the other way. And if you want to confirm, you can do it the other way. So we know our field is conservative. So we know it has components y e to the z and x e to the z and xy e to the z. And this has to be the gradient of some function little f for some f of x, y, z out there. And we know that there's such a function f that exists because the curl is 0. Now the only way that happens, the only way two vectors are equal is if their components are equal. So the x component of my gradient vector has to equal the x component of my field. And the y component of my gradient vector, which is the partial of f with respect to y, has to equal the y component of my field. And the z component of my gradient has to equal the z component of my field. So we want to get f back. So we'll anti-differentiate these with respect to the appropriate variable, and then we'll do some comparing. So f of x, y, z is the antiderivative of the partial of f with respect to x with respect to x. So I've got that. There are no x's in that, so it's just constant with respect to x. The antiderivative of a constant with respect to x is just the constant. And then we add something. It's constant with respect to x, but not necessarily with respect to y or z. So I'll put plus g of y and z. Now I want to recover f a different way. I'll take the antiderivative of the partial of f with respect to y, and we get the same thing. That's constant with respect to y. So we write down our constant and we multiply by y, plus a constant of integration. It's constant with respect to y though, not necessarily with respect to x or z. And then over here, we take the partial with respect to z. Whoops. Sorry, that looks like an f. And we take its antiderivative with respect to z. Well, xy is a constant. Antiderivative of e to the z with respect to z is e to the z. Plus, we'll say r of, it's constant with respect to z, but not necessarily with respect to y, r of xy. Now f has to be all 3 of these. So I can see by comparing them that all of them have this term. So f of x, y, z must have an x, y, e to the z in it. And then this function of y and z must be equal to this function of x and z, which is this function of x and y. The only way that could happen is if they were all equal to a constant. So I'll just say plus k, where k is just a constant of integration. Now, I don't really need the constant of integration when I evaluate a definite integral, though. So let's do this. Now that I've got my potential function, we can say the line integral over c of f dotted with dr is, f of x, y, z evaluated at the initial point and the terminal point. Now, the initial point was 4, 0, 3. The terminal point was negative 4, 0, 3. So we want to evaluate at the end point and then the starting point and then subtract. And this is our potential function. It's just x, y, e to the z. Well, y is 0. So we get 0 minus 0, which happens to be 0. Now, if you're saying that curve's not closed, that's okay. You could still get 0 because we evaluate the potential function at this point and this point, and we get 0 both times. Okay, now, one thing I did, but I didn't emphasize, was how I found these 2 points. To find the initial point, you just substitute in a right here. So r of 0 is 4 cosine of 0, 4 sine of 0, and 3. And that gave me this vector, 4, 0, 3. Now I'm just looking at the terminal point of that vector. That's where I start. So my starting point is 4, 0, 3. And if I evaluate this at pi, I end up with the negative 4, 0, 3. You can check that out. Okay, I know this video is getting pretty long. I think actually I will do the proof in the next video. I did want to show you one more thing or bring up one more thing. If you're wondering where all this terminology comes from, you guys remember this law of conservation of energy from physics class, from physics 1? If all of this feels a little bit familiar, it's because it should be, it is. Here's the law of conservation of energy. It says in a conservative field, and those fields that you studied in physics 1 and physics 2, electrostatic fields, gravitational fields, those are conservative. Now, electrostatic fields are pretty uncommon, usually charges move, but nonetheless, when we're just looking at electrostatics, we've got a conservative field there. In a conservative field, the sum of the potential energy and the kinetic energy of an object remains constant from point to point. I haven't gone roller skating in a while, but I always thought about this law of conservation of energy whenever I'm roller skating on Riverside and I see my potential energy converting to kinetic energy and my potential energy or kinetic energy converting to potential energy as I go over hills. Now let's say I have like a book right here, big old calculus book. I'm not very good at drawing books. That's supposed to be my calculus book, okay? Now if I lift it from right here to right here, if I lift it straight up, go from there to there. Do you remember what the work is from physics class? it was actually the potential energy at the initial point minus the potential energy at the starting point. Or sorry, at the final point. Now, if you're saying, why isn't it final minus initial? It's because the potential energy is not actually given by, the potential energy function is not actually given by the potential function of the gravitational field. It's actually the negative of the potential function for the gravitational field. That's why it gets flipped. It's like at the initial point minus the final point. But the work done, it just subtracts the potential energy here and the potential energy here, and that's all I do. I don't know about you, but I had many physics teachers do this in class. They say, okay, like here's my book. If I move it from here to here, if I move it from here to here, I've done a certain amount of work. Now, it does not matter if I like take this set of sticky notes and I move it all the way behind my back and I throw it up in the air, and then if I start here and I end here, it does not matter what path I move through. All I do is subtract the potential energy at one point from the potential energy at the other, subtract, and that's the work. That's it. That's all you have to do. Super simple. I don't have to take this straight line path. I can take any path I want. If I start here and end here, the work done is the difference in potential energy. Well, how do we represent work in Calculus 3? You're saying, I'd much rather do that. I know. I'm asking you to do something that looks a bit more complicated, aren't I? Work is defined this way. But that gravitational field is conservative. So this is equal to that potential function at the end point minus that potential function at the start point. And it's just convention that the potential energy function happens not to be the potential function for that gravitational field. It's the negative of the potential function. So if you talk about conservative fields and potential functions, maybe you want to tie these together in your head. Well, the conservative fields are like electric fields and gravitational fields, electrostatic fields, gravitational fields. They're associated with potential functions, which are very closely related to our potential energy function. Potential energy is is related to the potential function for the gravitational field. Or have you ever heard of electric potential, voltage? Same thing. That voltage function is closely related to the electrostatic field. So this is where that terminology comes from, and hopefully it can help you remember this. Now, try not to get too distracted by this sign difference. You're like, why is it initial minus final? And that's just because of a convention in physics class. Convention physicists have. For our purposes, you find the potential function, you plug in the endpoint, the start point, and you subtract, and that's going to give you the value of this. And that's also the work done if this is a force field. Okay. If you're saying that's going to be the wrong sign, talk to your physics teacher. All right. Okay, actually, I'm not going to make a separate video for the proof. I'll do the proof right now. It's very simple. So if our field is conservative, this is the proof for the fundamental theorem of line integrals. This is the same as this. Well, you know the gradient is this vector. And you know dr is just r prime of t dt. And rather than integrating over c, we'll integrate from t equals a to t equals b. So this is actually the same thing as this. And this will be dx dt, and then let's multiply by dt, and dy dt times dt. or actually no, let's not multiply by dt. Let's keep it this way. When I take that dot product, whoops, I end up with the partial of f with respect to x at x of t, y of t, times dx dt, which I'll call x prime, plus the partial of f with respect to y at x of t, y of t, times dy dt, times dt. Whoops, sorry, it's off the screen. You recognize this? That's a chain rule, guys. That's the derivative with respect to t of f of x of t, y of t. Well, what's the antiderivative of the derivative? It's the original function. And you evaluated a and b and subtract by the fundamental theorem of calculus. I just did this in 2D, but it holds this in 3D as well. Actually, ND would be fine. Let's just f at the end point minus f at the initial point. Very nice, huh? Just comes from the chain rule. Okay, this has been a long video, so I'll just stop.